About this though, and let's look at this idea. First, I just want you to understand, I just wanted y'all to get some ideas down, write about it. You've probably done this in your English or history classes before, where you write down everything you know about a topic just to get the ideas flowing and get you to remember, hey, this is what I've learned about this thing before, right? So, what have we learned about with multiplication before? What's some connections to the real world that we can think of? Zay, you had a pretty good one for earlier that I saw for a connection to the real world.
I see 5 close to each cat. Instead of 5 plus 5, 3 times 10, 5 times.
So if you're looking, and I assume that means you're looking at 3 cabinets, right? Then there's this idea, okay, if I have 3 cabinets with 5 cups each, then instead of doing 5 plus 5 plus 5, 5 times 3, which works really well when you start getting into maybe 20 cabinets or 17 cabinets or something like that, that multiplication can be easier than adding it that many times. So that real world example quickly reveals to us that multiplication connects to what idea that you've learned in the past? Adding, right? Right, so that's one of those things where I'm talking about when I say a connection to prior learning. And so you can write down that real world example. There's other real world examples that you can do, but a connection to prior knowledge would be the idea of addition. That's a big thing to notice, right? That's a very simple thing, but it's also really important. So when we talk about a personal definition, what do you think I mean? What did y'all come up with?
I see
Repeated addition, right? That's exactly what Zay was just talking about is, well, instead of doing 5 plus 5 plus 5, right? Just write 5 times 3 and be done with it. It's 15. All multiplication is a shorthand version of repeated addition. Now, I will say that's just a personal definition. There's some other small technical aspects that we're going to talk into the future about with this, okay? Because there is a proper definition. When I have y'all work through tasks, you're going to be talking through ideas, trying to learn together and construct ideas, which means you're going to come up with personal definitions, which are probably going to hit, usually they hit, a lot of the main concepts, but we'll talk about proper definitions later and some of the more delicate intricacies of things. But notice this 5 plus 5 plus 5 equal to 5 times 3 equals 15. That is an example, right? And so we got an example there. Usually I'll have you fill out the vocab after we've worked through a task so you can actually see other ideas or just reference a number from a task or something like that. And so that's somewhere that you could put the example. Like, for instance, we're working on 1.2 today. So maybe you could put for the examples 1.2 number 3. Notice that would tell you exactly where to look if you keep your notebook in order and you don't have to write the whole problem out. So you can say, hey, look at my notes at this problem, right? And that can help you a whole lot in studying and things like that. The other thing I want to point out is under the examples and notes, it also says connections within this unit. Because nothing is in a vacuum, nothing is an isolated idea. Everything you study, every unit will connect to some other idea. So we need to recognize what connects to what, okay? And so we want to make those connections later. And we'll look at some proper definitions for multiplication a little bit later. What about division? Did anyone come up with a real world application or connection to prior learning? No real world applications there, or
It can be 100 people in the store and 5 lines. Then you can like 100 people in each line.
okay. So 100 people in store and 5 lines. How many in each line? Now, here's the question I have for you though. What assumption are you making with that problem?
You divide like 100 into 5.
Well, you're not dividing 100 into 5, you're dividing the 5 into 100, right? But what assumption are you having to make when you do that?
Subtraction.
Say again. Subtraction is involved in it, yes. We're going to come back to that in a second. Caroline, what were you saying? How many people are in each line is the what? This, but what about those numbers? So right now, how many people are in each line? What are you assuming it is?
20.
So 20, 20, 20, 20, and 20?
Mm-hmm.
But what if it was 24, 28, 12, and 16? Is that a possibility?
Sure.
That's a possibility for 100 people in 5 lines. So what assumption are you making to make this division? How many people in each line is the what? Is this the answer to this question? What has to be true to answer this question? The number in each line has to be the what? What is 100 divided by 5? 20, right? So the number in each line has to be the same?
Yes.
See, these are the things you need to pay attention to. And so this is a great example, but I do want you to notice, right? Sometimes in order to make math work with the ideas that we're creating, you do have to make assumptions about things. Which, to be fair, if there's 28 people in one line, that wouldn't make a lot of sense if there's another line with 12 people. Because let's be real, when I get in line, I look at every single aisle and I find out which one's the shortest. Right? Don't you? So overall, it probably does balance out to be about the even amount in each line, but, you know, you have to recognize that you're making that assumption. Okay, so I think someone said subtraction. Was that you, McKay? Yeah, so we are connecting to subtraction. How?
Taking 100 and subtracting it.
Say again?
Taking 100 and subtracting 20 over 5 columns.
Right, so when we're dividing by 5, there's a couple different ways to read this. Dividing by 5, we could think of it as, what is 100 minus 20? 80 minus 20 again, minus 20 again, minus 20 again, minus 20 again. So how many 20s did I have to take out? 5, right? That is kind of the idea of division. You could take out 5, but it would take you 20 times to take 5 out, right? So we need to notice, because a lot of people just think about division as the inverse of subtraction, and it is. But also, right, we need to notice that division is, much like multiplication was repeated addition, division is repeated subtraction. That'd be a good personal definition. Now, is there going to be more to it than just that? 100%. But that's where the proper definition comes into play. Sorry, my mustache was getting up my nose and it was itching. Okay, so it's repeated subtraction. And we want to recognize that that's an important detail there. We see an example there that we can write. Again, you can make a note, hey, look at this example in blank. But I wanted to establish a couple of these ideas. One, about how this graphic organizer is going to work and how we're going to fill in some more information later. We'll talk about exponents tomorrow before we get started. Well, not tomorrow, maybe Wednesday. So today, we're going to start a task called Growing Dots. This is 1.2. It's to help us understand sequences and a lot of concepts you learned in Algebra 1 a little bit better. Because remember, this is kind of to prepare us to go from Algebra 1 geometry into the Algebra 2 is what it's designed for. So it's supposed to help us understand Algebra 1 a little bit better. And then we're going to do some small group exploration before we do a wrap-up discussion, homework, and looking ahead. So the objectives for today are, we want to be able to identify the rate of change for an arithmetic sequence. Has anyone ever heard that term before? You have heard arithmetic sequence? So just Alan, anybody else? Okay, that's okay. A lot of mathematics is developing a language and making sense out of things. you've actually seen a whole lot of things that are arithmetic sequences, you just didn't know it yet. So we're going to talk about it today, and it's all about the rate of change. We also want to be able to create multiple representations of a function. What do I mean by mathematical representations? What are the different ways that we can represent mathematics? We talked about it in some of this pre-assessment small groups. Anybody remember? It's also on the board. Already for my Algebra 1B classes. Well, we have recursive equations and explicit equations, but what is that underneath? Algebraic representations. When we say algebra, we're talking about expressions and equations and inequalities and things like that, right? An algebraic representation is what we're trying to work towards a lot of the times because it is probably the most efficient way to make sense out of a scenario, but what other representations are up there that can help us make sense of it? And how to write the equation. Don't everybody shout it out at once. It's not on the board or anything already. What other representations can you create or be given?
Graphical representation.
What do you think I mean by a graphical representation?
Graph.
Yeah, right? If you see a graph, it might tell you a lot about the nature of the function or sequence you're looking at. What else can you create?
Tabular.
Yeah, tabular and verbal. What do you think I mean by tabular? Yeah, say it louder. Tables. You probably called them XY charts or two-column charts or something like that. In middle school, they're called tables, though. Tables are really powerful. Verbal representation, meaning we're using our mouths. So what do we use our mouths for? To talk, to use words, right? Verbal representations, we're talking about words there. There is one last representation that I don't have up here, but it's actually what you start today off with, and it's pictorial representations. Sometimes we do struggle to see how things are happening, but a picture can actually tell us a whole lot. So here's the thing. I know, because I've heard y'all talk about it, a lot of us don't really love math or school in general. I get it. Here's the thing I need you to understand, though. School and math in general can help you appreciate the world that you operate in a whole lot if you understand the way that the math works. But one of those things is sometimes you have to change your point of view. In order to be able to get along with other people, to appreciate the people in your lives, the people in your life, there we go, that one, you have to change your point of view sometimes. Creating a new representation is changing your point of view. So we want to create multiple representations of a function to change our point of view to understand it a little bit better. And the biggest thing at the end is we want to write recursive and explicit equations for an arithmetic sequence. We'll look at both of those things today and look at what they mean. So, growing dots. Right? At the beginning, there was a dot. And at 1 minute, there were some more dots. And at 2 minutes, there were some more dots. So I want you individually to take 4 or 5 minutes. That's it. Right? To think about numbers 1 and 2. Go ahead and start working on them. If you get done with both of those, move on to number 3. After that 4 to 5 minutes, you're going to start talking with your groups to make sure that y'all are seeing things the same way. Any questions so far? What? You already got number 1? Cool. Move on to numbers 2 and 3. You're going to have 5 minutes or so. And if you get done with 2 and 3, then move on to number 4 even. But try to figure out what you can on your own. Then talk with the people in your group, and then we'll talk about it as a whole class. Okay, so right now we need to be silent, thinking and working, and we'll do some more later.